In this example, we have the blades of a wind turbine that are turning at an angular speed of 30 RPMs in the clockwise direction. If the blade length is 120 feet and they are given a constant angular acceleration of 0.2 radians per second squared in the clockwise direction, determine the angular velocity and the magnitude of the acceleration of point A at the tip of the blade when t equals 1 minute. All right, so we have the turbine blades. The length of the blade is L, which is 120 feet. We have this point A out at the tip. And initially, these blades are rotating at 30 RPM, but they are accelerating at a constant rate. So these are angular speeds and angular accelerations, but the equations are essentially the same as if you were dealing with linear speeds and linear accelerations. And since the acceleration is constant, we can use the constant acceleration equations. All right, so we're going to use the constant acceleration equations to find the final angular velocity, the velocity at 1 minute, and then use the fixed point rotation equations to find the linear acceleration of point A out there at the tip. All right. So the angular velocity, we have the angular velocity is equal to the angular acceleration times change in time plus initial. All right, when we use this equation, or any equation really, we can't use RPMs. We need to change it into radians per second. So that's what I did here. And then initially, the time is 0. And the final state, the time is 60 seconds or 1 minute. So I'm going to apply this equation at the final state and get that the angular speed at 1 minute is 15.14 radians per second. All right, then I'm going to use the linear fixed point acceleration equation that states that the acceleration has a tangential and a normal component. And the r in this equation is the length from the fixed point to the point that you're considering. And that, in this case, would be L. So I'm going to put that in there. And we know all of these quantities now, so we just plug in and we get the final value for the linear acceleration. Now, look at the difference between the tangential and normal acceleration. This is normal because it takes a lot more acceleration to keep something going in a circle than in a straight line. So you're going to see quite an acceleration in the normal direction. And notice that I have missed the square on the seconds here, so that should be feet per second squared.